Hello. So today we will discuss field theory of d-dimensional turbulence. We will focus on hydrodynamic turbulence, where velocity is only field. We'll assume that fluid is incompressible. Um, so it's a simplified assumption, and we'll try to illustrate how to compute the renormalized viscosity and Kolmogorov constant, as well as various energy transfers, energy flux using field theory. We will try to show that for d greater than 6, Kolmogorov theory appears to break down, and we will probably have equilibrium theory for d greater than 6. So let's start. We focus on Navier-Stokes equation. Here we assume, here the U is the velocity field, nu is the kinematic viscosity, force is the external force, and throughout the lecture we'll assume the force to be active at large scales. As in Kolmogorov theory, force is assumed to be at large scale. That leads to k minus 5/3 spectrum. Also, the flow is incompressible. So this is a constraint for incompressible, that del dot U is 0. Though some renormalization group calculations or field theory calculations are done in real space, but in this lecture we will focus on Fourier space, where these calculations are easier, or I would say more standard. So the U of k is Fourier transform of U of r, and this is a nonlinear term which becomes a convolution. So please recall that k equal to p plus q, k equal to p plus q. So we sum over all p's for a given k, and q is of course k minus p, and the pressure gradient becomes minus I k p, and force is Fk is Fourier transform of f of r. Divergence free condition leads to k dot uk is 0. Recall that pressure is computed by taking dot product of the whole equation with k, right? So that constraint gives us pressure, which is essentially divergence of, basically k dot fuk by k squared, and so this nonlinear term, we take the divergence, means the k dot of the nonlinear term divided by k squared. So it's just straightforward. You just multiply dot product the dimension, the evolution equation with k, and we'll get pk. Okay, so p is not an independent variable. P is computed by this condition. Okay. Field theory, of course, can be done using Cartesian velocity vectors, no issues. But it turns out we can simplify these calculations by going into Cray-Herring basis vectors. Okay, so what is a Cray-Herring basis vector? So let's look at it here. So we have vector k, any wave number k. Okay, this wave number k. Now we choose a vector n. It could be any vector. It could be magnetic field applied externally, gravity, or it could be just any vector n. Then you can apply k cross n. Okay, n hat. So we can make a unit vector along k, which is k cross n, which is E1 hat. Okay, so this is E1. E1 is pointing towards you, which is k cross n. You take vector k, which is in that direction, and k cross it, like that. Okay, so that will be k cross n. Then E2 is, okay, so E3 cross E2, E1. So what is E3? E3 is along k vector. Okay, E3 is this E3, each is along k hat. So we can do E3 cross E1 is E2. So where is it? It is in that direction, E2. So we have three basis vectors, E1, E2, E3. E3 is along K, and E1 and E2 are perpendicular to K. So for the incompressible flows, we know that UK is perpendicular to K, so that must lie in the plane formed by E1 and E2. Okay, so my vector U is lying on a plane formed by E1 and E2. There is a plane perpendicular to K vector, and it is the basis vectors are E1 and E2. Okay, so this is projecting that thing on XY space, but it's easy to visualize these two basis vectors of Cray-Haring basis in 3D. So in 3D we can write down any vector UK, incompressible vector UK, as a combination of U1 E1 plus U2 E2. Okay, so there are only two components and they are independent. Okay, that basically E1 and E2 are orthogonal and independent. This is discussed in many papers and many books. I am referring to my book where of course I discuss this, but which is not unique, but we also derive dynamical equations for E1 and E2 which are used for field theory. So that is derived in more detail in this book. So let's proceed. So it turns out these field theory calculations are very convenient to be conveniently performed for a triad. Triad is a basic unit, and then we integrate over all possible triads. Okay, so this is also done in standard field theory, so it's nothing unique. But it turns out if you just focus on a triad and write down the equations, it is more compact. So let's focus on a triad which is interacting triad. So we have three vectors K prime, P and Q. K prime, P and Q. So what is the condition? K prime plus P plus Q vectors, they sum up to 0. Okay. Some books write K equal to P plus Q, but that's asymmetric. So equations are slightly not good looking equations if I have asymmetry, but with this K prime PQ they look symmetric. Okay, so you can see that K prime arrow is in that direction, P arrow is in that direction, Q arrow is in that direction. Now I choose n hat. Remember we have n hat vector. So n hat I choose to be perpendicular to the plane formed by these three vectors K prime PQ. So it is here. It is perpendicular to the plane pointing towards you. Okay, so it is pointing towards you. Now what is E1? K prime. So for every vector K, every wave number, there will be a unique E1. Okay. So for this vector K prime is in that direction. So K prime cross n. So K prime cross n, like that. Okay. So when I do the cross product, so K prime cross n, so it will go upward along y direction. In this here, this is E1 K prime. So similar operations leads us to other two E1s for P and Q. So they are perpendicular to these wave numbers and also perpendicular to n. And you can see the red arrows are those E1 wave vectors. In 2D, that's it. We'll have only E1 K prime, E1 P and E1 Q. But what about 3D? In 3D, we have one more component, right? Which is that component? It is E3 cross E1. Okay. So E3 for, let's say, K vector is in that direction, K prime is E3. So E3 cross E1. So you do cross product like that. So it is into the plane. So that is E2 K prime. Into the plane, which is opposite of minus n. So this minus n vector. Same thing for E1 and E2. So we have E2k prime, E1, E2p, E2q, they are all perpendicular to the plane of this triangle and into the surface. So great. How do I write equations? Well, now we have U1 component and U2 component along E1 and E2. In 2D we have only U1. In 3D we will have both U1 and E2. How do I write down the equations? So we will not do it here, but I'll show you how to do it. I'll sketch how to do it, not show you. So this is U vector, okay, U of k. So right hand side will have various terms. So take a dot product of this with E1 of k, k prime. Take a dot product of this full thing along E1 of k prime. Alright. So left hand side this is dt of E1. The right hand side, the U dot grad U, we need to do the projection along E1, and it's bit of algebra. This convolution, well, right now I'm working with single triad, so there is no convolution, but there are convolution in the sense we'll have U1p, U1q, and then U1q, U1p. So if you do the algebra properly, which is there in this book, you will get this ik prime sine beta minus gamma U1 star p, U1 star q. Okay, look, it looks nice. We don't have tensors, very complex expressions, pressure is gone, and that's it. The viscosity is sitting here, which is shown here. Similarly, we can round down equation for U1p and U1q, and you can see it is symmetric, beta minus gamma, gamma minus alpha, alpha minus beta. And the wave numbers in the right are not what is there in the left. So if I am looking for U1p, then this is U1q, U1k, k prime. Okay, and these are the forces. So this is nice for a single triad, and we just work with this expression in the right. Similarly, we can write down equations for U2, which is into the board, d by dt of U2k prime, U2p, and UQ2, and this is slightly more complex. So these are the expressions. Okay, it's a bit of algebra, but nothing very complicated. Okay, now let's go further. So what about d dimensions? This is for 2D and 3D, right? 3D we have U and U2. So for 4 dimension, how do I visualize 4 dimension or 5 dimensions? So let's look at it slightly carefully. So these bottom diagrams, these 2 diagrams together make a 5-dimensional space. How does it make 5-dimensional space? So let's think of vector k, which is the red vector. So first, this is first unit vector. So this is E1 unit vector. Okay, well, it's a you can call it x vector. So its components k1. Now, so here I take this vector k and I project it along this axis. So I'll get this as k1. This part is k1. Now I project it in a plane perpendicular to well, I'll project it perpendicular to k. So I'll get this vector. Okay. Now this is my sitting here. Now project it along second axis. So this is k2. Okay. If this angle is phi 1, the angle is phi 1. So this is k1 sine phi. Well, this is k1 cos phi 1, and this is k1 sine phi 1. So I got k1 sine phi 1. I project it again. So that will be k1 sine phi 1 cos phi 2, and this is angle phi 2. In that direction, I'll get k1 sine phi 1 sine phi 2. So this is, now had it been 3D, I would have called this as k3. But I'm working in a 5-dimensional space. So this is, we call it k perp. Okay, K perp is not along any axis. K perp is still floating around in that space, 5-dimensional space. So K perp is this vector. Okay. So now look at a space which is perpendicular to K1 and K2 plane. In 3D it would have been just K3, but in 5 dimension it has K3, K4, K5. It's a volume. So now K perp I project it along K3, which will be K perp cos phi 3. See, we have K perp cos phi 3. So this is, and K perp we already know it is this. So here will be K sin phi 1, sin phi 2, cos phi 3. Now this is projection on K4, K5 plane, okay, which is going to be sin phi 3. Now again projected along K4 and K5. So these guys is along 5th K5 and this is along 4th axis. So this is how we project it. Now had it been 6-dimensional space, then this won't be the 5th axis, but this will be a vector, and we project that into K5, K6 plane. So we can continue this operation like that. Okay, so this is how we construct components in a d-dimensional space. Now let's stick to hydrodynamics only. So how many, so what about Cray-Haring basis? So 3D we saw that is U1, E1 plus U2, E2. But in 5 dimension, how do I do it? So we follow the same idea. So we can choose n cap along that direction. So K cross n cap will be perpendicular to this. So perpendicular to this plane. This is the plane here. It's perpendicular to this plane towards you. Okay, the perpendicular to the plane. Now E2 will be in that direction, perpendicular to n cap as well as E1. Then what about E3? So in 5-dimensional space, we have more components. Okay, so compared to perpendicular to E1 and N, we have 3 more components, or in fact 4 more components. So E1, E2, E3, E4. Okay, so total we have 4 in 5-dimensional space. Right, it's incompressible condition, so one of them will go away. So we have 4 components in thing. So this is U1, which I showed you. This is U1 perpendicular, but U2 is perpendicular to E1 and n cap. So we got U2, U3, and so on. In d-dimensional space, we will have U2 to UD minus 1 as a vectors perpendicular unit vector. These are components. So we'll have E2, E3, ED minus 1 like that. So these guys are all perpendicular to E1 and they're perpendicular to each other. So this, in fact, they're orthogonal stuff. And the components along these unit vectors are U1, U2, U3, and so on. Okay? And if I take the mod square, then I'll get correlation of the component. So this is U1 mod square. So this is, in fact, I can call it C1 of K. This is C2 of K, C3 of K, and so on. So we make a notation, it's called Cu of K. So first, for isotropic flows, which will be assumed for this lecture, for isotropic flows, all the components have equal energy. So we'll say that U1 squared, U2 squared, U3 squared, all of them have same energy, and that is Cu of K. Okay, that is what we here got. Now, this is also called, well, it's a component. Okay, so C of K is energy of a component. It's not the total energy. A total energy, I need to sum it up. Okay, so I need to sum up all the CUKs over all dimension, then that is C of K. So we work with the component, it's more convenient. Now we have one more important energy, it's called one-dimensional energy spectrum. So E of K is a one-dimensional energy spectrum. And what does it mean? If I integrate, so it is, we make a shell in d-dimensional space, this one, okay, and if the radius of the shell is dk, then ek dk will be the energy contained in that shell. If I integrate over all k's, then I'll get the total energy, total kinetic energy of the volume. So this is the u squared by 2, and that is equal to ek dk. But we also know what is the total energy in terms of components. So there are d minus 1 component, so d minus 1 times uk, and I integrate over whole volume. This is the whole volume. So dk, and okay, one more thing, this 2 pi to the power d. This is a prefactor which floats around in field theory all the time, and this is connected with the Fourier transform in infinite box. So in Fourier transform in finite box, we'll have 1 by volume of the box, but in infinite dimension the volume is infinite, so we work with 1 by 2 pi to the power d. We will not get into it why it happens, but you can look at standard book where you can find this origin of 2 pi. Okay, so we have expression for 1D energy spectrum and modal energy, well, energy of a component C of k. Okay, and well, it turns out this is function of k. Now for isotropic flows, it won't be function of k vector, it's going to be function of k magnitude. Okay, so it's isotropic, so any direction I go, I will get the same energy as long as my magnitude of k is fixed. So here I can integrate over all angles, and we get simplify this. The relation between E of k and C of k is this. Okay, so this is useful when I do the field theory. So that's why we have written this equation for reference. Now we can invert this equation to write down CUK in terms of EK. And please note that for non-equilibrium solution, E of k is k minus phi third, and there is a Kolmogorov constant prefactor, non-dimensional constant, and this epsilon is the energy supply rate at large scale. So imagine I have a fluid which is in a big box of size L. Well, we'll make L go to infinity because we assume that there's no boundary and so on. So this energy supply at a large scale, and that goes down to a small scale, and and this is cascaded. This is a energy supply rate from large scale, which is epsilon. Okay, so this is a framework, and we look for situations when this phi third is a good solution of our equations. Okay, now the nature of solutions, we expect two kinds of solution. One is this phi third solution. For energy spectrum, we get k minus phi third, or not or. The viscosity right now, ignore u1 right now, this new exponent right now, well, the subscript, and from here we can derive what is nu of k. It has dimensions of velocity scale, u of k times length, k inverse. Okay, and in Kolmogorov theory, this is epsilon 1/3, k 1/3. So my k minus 1/3, sorry, k minus 1/3. If we substitute this, then I get k minus 4/3, epsilon 1/3 is a functional dependence in terms of epsilon and k. But there are prefactors, so we'll have nu1 star, which is a constant, which we don't know, we will like to compute it, and this k0 square root, Kolmogorov constant square root. We keep it that way for reasons that will become clear. When I compute this RG equation, it turns out if I use this form for viscosity, my Kolmogorov constant gets cancelled. And with RG, I can compute nu1 star. Okay, it's not dependent on nu1 star. Sorry, it is not dependent on Kolmogorov constant. Nu1 star is outside. There is another solution called equilibrium solution, where this every component, this is not a function of k. So C of k is constant. Here is k minus 5/3, but here is constant. So we say the modal energy for every k is constant. Okay, and we'll say that viscosity is also 0, or viscosity is not corrected by Rg. I'm going to come to that a bit later. So we'll focus on a triad. We have discussed this triad before, and we'll compute my correction, or will some quantities for a triad in a plane, and then we'll integrate over all planes. Okay, so we'll say, well, I shift the plane, then my n cap will change, but I again get, if it's isotropic, then we expect things should be, I just need to integrate and average. Okay, that's what we will do. So that's the idea. This is for 3D. So we have k vector is fixed. Now I'm going to sum over all p's and all q's. Okay, so sum over all p and all q. So in normal field theory, is dp dq. Please remember that q is k minus p. But in this presentation, we are going to make change our stance. We are going to use, well, by the way, this will involve integral dp dq. Okay, is the magnitude of dp. So once I fix magnitude of p and magnitude of q, my triangle is fixed. In this presentation, we will use dp d gamma. So this angle gamma. So once I fix gamma and p, then q is fixed. So it turns out this is easier to handle. That's what I am propagating, that this is easier to handle. In fact, z is a variable called cos gamma, and in fact we are going to use dp dz. Okay, so dp dz, that's what we'll use, and we find it's convenient. Expressions are nice. Asymptotic analysis is also easy. More convenient with this. Okay, so now this is a preliminary work. So we set up Cray-Haring basis. We showed how to write equations for a triad, and then we also showed how to do an integral. Well, yeah, how to sum over all Weyl numbers. So let's write down equation for u1. This is equation for u1, right? We derived it before. Well, I showed you how to derive it before. And we have this u1, and right hand side is coming from non-linear term. This is viscosity. I'm going to say that viscosity for u1 and u2 are not equal. In fact, we show that they are not equal. So we'll start using nu1 for u1. So viscosity depends. For u1, I need to use nu1, and for u2, I need to use u2. So it may look pretty odd because in numerical simulations we only use one viscosity. But in RG is not same as numerical viscosity, by the way. So it's a coarse grained viscosity, and it could be pretty complex function, and it could depend on the component. In any case, this is what we get from formalism. Okay, in some sense, these news are connected with large area simulations, and we may claim that okay, I can take some average of nu1 and nu2 for my RG. So let's look at it, how to compute this viscosity in renormalization group. It's a function of scale, or okay. So the basic idea is that we start with this equation, which written in the previous slide, but this nu will be a variable. So okay, now let's focus on this idea more carefully. So we'll assume that my forcing is somewhere here. Okay, my forcing is somewhere here. Well, it could be here. Let's imagine. Okay, force. So when I focus on this Weyl number or this Weyl number, this f1 is 0. So this is gone. Now, okay, this is a pretty tricky part. Uh, my smallest wave number, largest wave number is somewhere here. K infinity, call it. Okay. For water, uh, the fluid structures exist up to millimeter, like coffee cup, you know. So K infinity is here, but I would say, well, I already started looking at scale bigger than K infinity, much bigger than K infinity. I am somewhere here. I am in the inertial range. So where in the inertial range, my viscosity has already changed. Okay. So we are going to use iterative procedure, iterative, or recursive procedure. So we'll assume that I am here. I have already done some work so that I can get effective viscosity at this scale, and that is nu n plus 1. Okay, and we will fix k to be, okay, so that's what we'll do, nu n plus 1, and this k squared. This nu n plus 1 k squared. Okay. Now, next idea is that, so I have these modes already gotten rid of. Now, if I go to this scale, Kn, the viscosity here will be, this scale is nu n. Okay, so I should get rid of this, this k squared. So this is nu n. So when I go to this scale, I would like to see what's the difference between nu n and nu n plus 1. If you can get a relation between nu n and nu n plus 1, then I can say, well, this formula should hold for all n in the inertial range. So that is a recurrence relation or recursive relation, and assuming scale invariance, once I get that relation, then it is valid for all n's. Okay, so that's the whole idea. We want to derive the recursive relation. Okay, so viscosity increases as you go from go to lower wave numbers and a larger scale. So when you go to the left, so lower wave number is going to the left, and we get larger viscosity will show that it increases with the wave number. Okay, now so as I said, viscosity, in fact, we'll try out this function, which is consistent with Kolmogorov theory. Okay, and we'll show this using the perturbative RG. Right. So yeah, so we want to look at relationship between nu n and nu n plus 1. Okay, this algebra in general is quite complex, but we'll use our gray herring basis, and I'll show you that it does simplify the algebra. So typical RG involves, okay, now we need to step back a bit. I'm not going to cover different RGs, but we just need to relate it with the previous work. So there are 3 parameters which are renormalized in typical RG procedure. So what is lambda? Lambda is the coefficient in front of u dot radius. In Navier equation, you start with 1, but you should think that this lambda equal to 1 is when we keep all the Fourier modes, means all scales. But when I go to reduced scale, then there is no guarantee that lambda should be same, right? When I look at a picture which is at very small scale, it may look different than when I look at it large scale. Okay, a character of a human being differs when at what angle do you look at it. So this lambda may differ at different scales. So, so people look at how lambda changes, how viscosity changes. In fact, I have told you in the previous slide that we are trying out solution when viscosity goes as nu k minus 4/3, and forcing amplitude also. Okay, so it turns out I'm going to try some forcing amplitude. Well, in our simulation, in our framework, we are not worrying about forcing, but in some other work, people force at different scales, and then this forcing changes with scale. So these are the three parameters that change with scale. But it turns out Navier-Stokes equation has some interesting properties. Okay, lambda is not renormalized due to Galilean invariance. So lambda is unchanged. Okay, it's a pretty interesting property which is not so trivial, but you can look at some books, for example, Mecom. So it doesn't change with under renormalization. Okay. Now, before I get further, I should say that I am going to adopt Eulerian framework. That means we just stick to fluids, not with particles or fluid parcels, which is Lagrangian approach, and it has certain merits. It is simpler, but people are objected to usage of Eulerian framework, like Crichton said, the sweeping effect, which is not captured by Eulerian framework. But Eulerian framework is successful to large degree, so stick to Eulerian framework. So I'm not going to get into that aspect. We are using Eulerian framework. So as I said, we are going to see how viscosity nu changes with scale, and okay. So in fact, we are going to just focus on nu. And I said before, my forcing is at large scale. It supplies energy flux, and we are not looking at forcing at intermediate scale. So this is also gone. So among three parameters, I just need to focus on nu renormalization, which is interesting. We don't need to worry about other two. And we will try a simpler scheme, which is called self-consistent procedure. So we will try to see whether phi-3 is a solution for the RG equation, which is going from nu n plus 1 to nu n. Okay, so detailed calculation. Okay, so our starting point is this equation, but with a minor modification that this is nu 1. Okay, so this is a viscosity of corresponding to U1. Okay, so as I motivated before, of course my wave number starts from k infinity, but I have done something and gotten rid of it. I am here. My viscosity at that scale is nu n plus 1. Okay, and what are the modes available to me? Fourier modes. So we have lots of Fourier modes all over, right? These are Fourier modes. So I am interested to see what is the viscosity at Kn. So these modes, I call it less variables. Okay, they are less variables, and this is greater variables. So I am going to average over this. So imagine this corresponds to 1 centimeter scale, and this corresponds to lower wave number, that means higher scale, 5 centimeter scale. So you can think of I have a microscope. One of them looks at 1 centimeter scale and bigger, not smaller. Okay, 1 centimeter and bigger. Other one has a resolution of 5 centimeter. It cannot see 1 centimeter. So 5 centimeter resolution. So when I look at through a microscope, which is 5 centimeter resolution, I am missing out some things. Okay, so the missing variables are called greater variables. So when I look at 5 centimeter scale, there are some interactions among modes which are between 1 and 5. Okay, so this is greater variable. So of course we have convolution. So convolution has 4 types. So it is here U less, U less. So P and Q lie here, or P lies here and Q lies here, or P lies here and Q lies there, or both P, Q lie here. Okay. Now due to lack of time I will not prove it, but I can show that these two are zeros. Less greater and greater less are 0, and we are left only with greater greater and less less. Okay, and please remember that my viscosity is nu n plus 1. So this equation, when I do averaging and my field theory, these are gone. Now when I look at equation for when I have only dissolution up to 5 centimeters, so that means these modes are already gone. When I have that situation, then my viscosity will be nu 1 n, okay, this one, okay, and we have my velocity field is basically from here to here, okay, here to here, and I'll have less. These things are gone. Okay. So it turns out this is non-zero. Okay. So what's the difference between this equation 1 and equation 2? Is a okay. Just look at the equation. So right hand side, this part is copied here. This part. Well, this part is already gone. So this part is here. D by dt is also there. Here my nu n plus 1 has changed to nu n, and this term is missing below. This term is missing at the bottom. So basically my new viscosity nu n k squared, nu 1 n k squared, is this component, and I take this to the left hand side. Okay, take it left hand side. So second integral of the above equation. Okay, this one. By the way, there is an integral here, huh? So this integral continues for all of them. So, well, I am ignoring this, so I am calling it first and second. Second integral goes to the left hand side. Okay, and so add that to nu n plus 1 k squared. Second integral will subtract because it goes to the left side. This is nu n k squared. It turns out the second integral is a negative sign. So negative becomes positive. So nu n plus 1 k squared gets a positive addition of a positive number. So that's why nu 1 n is bigger. Okay. So this is what we need to show. So in fact this is very interesting. I am able to get a recurrence relation. So given nu n plus 1, I can get nu n by this procedure. So and we can continue this to the left, but we don't need to continue. If I get a recurrence relation, I can solve it, and I can predict for viscosity for any n. Okay, so let's see how it. So this is what I wrote in the previous slide. Now, the idea is to compute that u greater p, u greater q. This integral dp. This integral has to be computed. Now, to zeroth order, so remember you have u greater p, u greater q. If I do the averaging, so by the way, this is a integrand. Well, I mean that is so variables you need to see, which is changing with time, changing with space, So there is a time as well, so please keep in mind there is a time as well, but they are equal time. If I assume u greater and q u greater p and u greater q to be random variables. Now I am assuming that this velocity field has no mean, its average is 0. So these are random variables with 0 mean, and if you assume this to be totally uncorrelated random, then this is 0, unless Q is equal to minus P. So if this is minus P, then this is if that is the case, then it is UP mod square. Okay. So it turns out if Q is equal to minus P, then K becomes 0, and that's the mean flow. So that's not possible. So it turns out to 0th order this quantity. So second integral, this second integral is 0 to 0th order, assuming U to be random, and in fact called Gaussian approximation. The whole thing approach is called Gaussian. If this guy is 0, okay, then my viscosity is not changing. And what is it? What does it mean? So if my velocity field is totally random, uncorrelated, the viscosity doesn't change, and this is called equilibrium solution. Okay, this has been seen. It's like thermodynamic gas. It's also seen in Eulerian turbulence. So this is the situation when the equilibrium solution and viscosity you can treat as 0. Okay, so that's a trivial solution where there is no renormalization, viscosity is 0. This corresponds to Gaussian approximation of 5-4 theory. Okay, that's correlation. That's a connection. However, if I look at non-trivial solution or equilibrium solution, then we need to look for higher order. We want this to be non-zero. In turbulence, in real turbulent flows like atmosphere or in coffee cup, boilers, this is, this integral is, we know that the viscosity changes with a number. So this integral must contribute something. That means U greater, this integral with instead of less you put greater, that should contribute something. Okay, that was in the previous slide. I can't go back, but that integral dp U greater P, U greater Q at same time must be non-zero. And how do I show that is non-zero? So to 0th order it is 0. If I average, well, by the way, this turbulent flow has so much fluctuation, it doesn't make sense to compute things for a given time. It's good idea to average over similar times. Okay, so I need to go to the next order in perturbation. So like Taylor series, no, you do perturbation to 0th order, then x squared. So I want to expand this. So how do I expand this? So you can say that I would like to expand U. So I write what I like to see what is U greater P as function of time itself. So this is that equation. Okay, so if I delete this rough work, but so this equilibrium solution I have written it here. We'll get back to it a bit later, but let's get rid of this one. And now let's start again. Okay, so U greater P is so we have equation for U1. Remember the equation will be d by dt of U1 like that. So we can write that in terms of Green's function. So d by dt. So there is a way to write differential equation solution in terms of Green's function. So this is the Green's function Gp t minus t prime. This vortex for P is going to be IP, and this convolution integral, okay, is coming okay, dt prime, and this is what is there in front, this guy, and we have U1 R and US. Okay, so this is a convolution part. Okay, so I have missed out this 2 pi 2 power d here. This should be there. Okay, so but yes, so we write UP is solution of UP in terms of more variables. So this object is written in terms of Feynman diagrams like this. So this Green's function is written as, so remember we had two of these guys, this stuff, and this called vortex, this vortex, okay, this vortex, and this object is this ik prime sine beta minus gamma, this one. Okay, so this is what I have written here, and this is u of p. So let's use a slightly thinner pen, and I'm going to use this color, this color, this color, and this is u1 of q. So the u1 p I am expanding, so this is vortex, is the Green's function. This is called Green's function, okay, this is Green's function, and it has two legs. Which are two legs? UR and US. These are two legs. UR, US. And we got UQ here. And the subscript 1, but we don't worry about the subscript 1. So how do I solve it? If I use this to be Gaussian, three of them, and there is a property of Gaussian variable, x, y, z, if they are Gaussian variable, that is 0. Odd order is 0. So it will be 0 unless, in one case it will not be 0. When it is not 0? When we have uq and us, they are complex conjugate of each other. That means when s is minus q. Okay. If that is the case, then if s equal to minus q, so let's get rid of this object. If s equal to minus q, for that particular case, I can write it, these two guys come together and make a correlation function. And you can easily see, in fact, let me write it here. What is R plus S? R plus S is P. Right, because it's a convolution condition, so you're writing P. And if S is minus Q, then what is R? R is P plus Q. P plus Q. So what is P plus Q is K. So the U of R becomes U of K. And K is in the less regime. So we are looking at wave number in the left of Kn. Okay, so that is what we got. So this is my integral, the first integral. Okay, and so that's what we written here. G Green's function, which is Green's function here. Correlation function, this correlation C of Q, this object. Correlation function here, and u less k. You can focus on the time, which is small here, this t prime here. So t minus t prime, and these are vortex, okay, there are two vortex. One vortex here, one vortex here. And this is also called bubble diagram or a loop, bubble diagram, okay. So it's like bubble, no? So we have bubble diagram. One side is Green's function, other side is correlation function. Now this is I1. Similarly, we can compute another integral. What is the other integral? So if I use the red color, so I can expand. So here I use the u and p as the Green's function, but why shouldn't I use u and q as the Green's function? If I use u and q as the Green's function, then I get, what do I get? I get the second diagram. So u and q is the Green's function, then I get two arrows here and one arrow here. So I combine these two, I get correlation function, Green's function, and this is u less k. Okay, so there are two diagrams which are coming because of perturbation. I expand u1 of p, or one diagram, and expanding u1 q, I get another diagram. So I have two integrals, I1 and I2. So I2 have, I'll show you in the next slide. Anyway, so we got this integral I1. It's still complicated because we have t minus t prime, we have qt minus t prime, and this integral and this dt prime. So now we make one more approximation. And what is that approximation? We assume that this Green's function and correlation functions decay quite fast. Okay, so it will be basically these functions decay very fast, they drop very fast like that. So this integral, which I will not bother you with the details, it gets a contribution at very small time only. Okay, when t equal to t prime, that region only it gives, t near t prime, that its contribution, and it's very small. When it is very small, this object is big, nu k squared is big. Okay, that's when exponential will be small, right? I mean, e to the power minus gamma t, gamma large, so the time scale is 1 by gamma. Okay, for that particular situation, we simplify that equation, but look at the form. So this is the correlation function, which is function of t minus t prime. Now g1, Green's function, is dropping as e to the power minus nu k squared t minus t prime. Correlation function also drops with the same temporal behavior, and the function in front of t is called equal time correlation. Equal time correlator. Okay, that is C1k. So it is a same time, and this is a different time. So different time is, I use, well, some places are written hat, but is C1 bar. In the diagram is C1 bar. Okay, if I substitute it in that integral, in the top integral, this one, then it becomes much nicer. So let's erase this part. So you see it has these objects. This integral gives us nu1 p squared and nu1 p squared plus nu1 q squared, and it turns out, well, we are only dp integral, no time integral. Okay, so this is where we are. The second bubble diagram shown in the previous slide gives you this. Okay, they are similar looking expressions. Still, we need to get a number for the integral. Okay, otherwise I can't get a recurrence relation. Okay, so what all we have? This is correlation function nu p. I don't know how they look like, what they are. Without that, I can't figure out. I cannot solve that integral. Okay. However, if you could get this expression I1 and I2, then I will get this equation. Nu1 k squared is nu1 plus k squared. So please remember that, let's write it here, I think it's here. So, well, this is the expression, okay. Now, the quantity of concern is these guys and this nu1 p, functional form. So, in self-consistent theory, so let's call it self-consistent, I'm going to use the other color. Self-consistent theory. We'll assume some form of nu1 and CUK and see whether this solution satisfies this equation or not. Okay, so what is form of EK? We use this k minus 5/3 Kolmogorov spectrum. Okay, and we'll see whether we are getting some useful, well, rather consistent solution or not. And nu and k is k minus 4/3, and there are constants in front. Okay, so substitute these, then if I substitute them, there will be constants and some function of p, q, power laws, but they could be integrated. Now, region of integration, that's another thing to worry about. So the deep integral, where I am integrating. So remember our integral is kn to kn plus 1, right? So it is kn to kn plus 1, this region only. Okay, so to simplify the algebra, or to do things slightly in a concise and compact manner, let's get rid of this. We make a change of variable. So we make a change of variable, saying that p is kn times p prime, and q is kn times q prime, and p prime, okay, see, p is bigger than kn, so p prime is going from 1 to b. So what is b? B is kn plus 1 by kn. So maximum value p can take is kn plus 1. So p prime can go up to b, right? So that's what so p goes from 1 to b. Okay, so p goes from 1 here to b. Q also goes from 1 to b, but my variables are not p and q, my variables are p and z. So z is cos of gamma, and it is easy to verify that gamma takes these two values. Minimum gamma is minimum z is this, and max z is that. So this is integral, and it's a bit of algebra, but this is what we get. Okay, and f1 and f2 are some functions of p prime and z. Okay, and this SD is the area of the d-dimensional sphere. For 3D is 4 pi unit sphere, d-dimensional unit sphere. So 4 pi k squared for k radius k, but for unit radius is 4 pi. SD minus 1 for 3 dimension will be S2. Here the sphere is a circle, which is 2 pi. Okay, so anyway, so this integral is there. Now remember nu n plus 1 will be what? So if I put here, so that will be kn plus 1, right? For nu n plus 1, it will be kn plus 1, and that will have factor b. Okay, and nu n has k, so that will be kn. So it turns out, if I do the algebra, there's an additional factor of b to minus 4/3. Okay, that 4/3 comes here. So in the left hand side, if I take this to the left hand side, here I get nu n square b minus 4/3. Now why this nu n squared? That's another interesting aspect. So look at it here. So here I got correlation function. Okay, so correlation function will have in here k Kolmogorov, this Kolmogorov constant k. Correlation function is proportional to ek, right? This ek. There is nu below, so that will be square root k Kolmogorov nu star, this one. Left hand side also has a nu n, so left hand side will be square root k Kolmogorov. Well, I mean, this part has the stuff, so this goes to the left, and it turns out Kolmogorov gets cancelled, and one nu star in the left and one nu star in the right. Well, one by nu star in the left, in the right, and nu star in the left, so that becomes nu n square. Okay, so beauty is that this correlation function has a k Kolmogorov constant, and this nu one and the left nu one are also a Kolmogorov constant, they cancel. So that is why that square root of k Kolmogorov is chosen. So we solve one constant at a time. Okay, so we solve nu one star by this equation. Okay, now is there in my paper, this f1 and f2 are there for u1 for any dimension. So remember, these equations are written for any dimension, and we can get nu one star by solving this equation. Well, I solve this integral and I get nu one star. This integral is solved in Python using Gauss quadrature. Okay, and rhombus method. Okay, so not rhombus. We solved using one of the integral schemes. Okay, so Gauss quadrature is one, and the other one is another complex integral. But these functions exist in Python, and it can be solved. This is for 2D. So we'll come and look at the solution in the next slide, a few slides down the line. Next, we look at nu2. Okay, so that was a vector perpendicular to the plane, and it turns out, you can look at the diagram. The two legs are u1p and second leg is u2q. The previous slide both were u1, but here it is u1p and u1 greater u2q. Okay, and you can easily see, well, I mean, this is a nice thing to see. Here, well, at this point, u1, if I expand Green's function, I'll get two u1s, and here I get u2, and here u1 and u1. If I expand the top, u2, u1, if I combine, it could be non-zero only when there is a helicity, hk not equal to 0. But if helicity is 0, then this is 0. So expansion of this is meaningful only when there is a helicity. In our work right now, we assume the helicity is 0. So u1 we need not integrate or need not expand. So this expansion is not required, and we expand only the bottom one. So we expand only the bottom one. So u2 expansion, Green's function, and 2 u's. It turns out 2 u's, one of them is u1 and another one is u2, and one u1 here. So these two are combined together. That's a correlation function, and this u2 becomes k prime. Okay, so nice. So this is u2 k prime. So the Green's function, and this is correlation function and Green's function. Remember both of them. Well, this is for component 1 and this for component 2, because I am expanding u2. So this will be g2. Similarly here, I expand u2 above and correlation function below. So anyway, so very similar procedure, same perturbation scheme, and we get closed form solution. So the integral here, I3, coming from these integrals, is here. Exactly same thing we need to do as before, and we get nu2. Oh, I'm sorry, I forgot square here. No square. Apologies, no square. Because at the bottom, this one has nu2 and u1. Okay, so here we have Green's function, so of 2. So 2 Green's functions gives you nu2, and correlation with 1. So correlation 1 gives you that. So anyway, this is the expression. Nu2 star is integral with f3, and f3 has nu2, nu1. So this integral is function of both. Right hand side is nu2 and nu1. So what do? I need to do iteratively. So we can solve it iteratively. and it turns out it has a solution. I will show you what they are. So I did solve it for various dimensions from 2 to 6. I went up to 6. So it turns out this is a new one, and these numbers are around 0.1, okay, 0.09, and slight decrease, but it's basically close to 0.1, and nu2 is around 0.6, so nu2 is slightly above here. So you see these two components have different viscosities. Please keep in mind that nu2 star and nu1 star are not viscosities. Viscosity is nu star, 1 star, 2 star, square root k Kolmogorov, epsilon 1/3, k minus 4/3. So this is a viscosity. We have prefactor in front, which is given here. Okay, so we can find that. Now, interestingly, so this goes up to 5.5. At 6, the equation for nu1 squared. So we have equation for nu1 squared like this: 1 minus b squared. Right hand side, da, 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 da. It turns out the right hand side is negative. So what does it mean? This is squared. 1 minus, b squared minus, no, this is b 2/3. 1 minus b, b minus 4/3. So this is minus 4/3. So this is less than 1, okay? This is less than 1. So it turns out this is positive, but right hand side is negative. So it has no solution. I will try to get iterative solution and see whether we can get 0 as a solution. Okay. But in any case, we find that at present there is a contradiction. So nu1 has no solution for d equal to 6. So that's where I believe that at d equal to 6, this is not, the Kolmogorov is not a solution, Kolmogorov minus 5/3, but nu1 equal to 0 is positive, is a solution. Well, we know that is a solution, but whether it's a stable solution, whether 5/3 is unstable, so that needs a bit more work, which I have not managed to do it so far. Okay, so we are able to get these renormalized viscosities for various dimensions, and up to 5.5 or maybe 5.7 as well. But so look, in this integral I can put any dimension. It need not be an integer dimension, and so we are able to see this variation. Okay. 6, probably the variables are Gaussian, and there's either 0 flux or very little flux. Okay, so that's my feeling. So our flux is possibly epsilon may go to 0 for d equal to 6. It's hard to verify numerically, but okay, anyway, that's a prediction of this theory, which is a valuable prediction. Okay, now let's look at quickly energy flux. So how to compute energy flux, and that in turn gives us Kolmogorov constant. Okay, so that can also give you K Kolmogorov. Okay, so the idea is to start with energy, the equation for the energy evolution. So the energy evolution equation is this. Okay, the right hand side involves convolution, and we got a pretty complex equation. UP UK star and K dot UQ. It turns out this one has a nice interpretation. It is energy going from P to K with Q as a mediator. Anyway, so this is the expression, and I need to sum over all P's. So this is also called Tk. Okay, this is also called T of k. This object is called T of k. A pressure is not appearing here. When I take a dot product, the pressure goes away. And ignore this, forcing is not in the inertial range, so we ignore it. So we need to compute properties of this object. Okay. So we have, I wrote in the previous slide, what is this K prime PQ. So if I use Cray-Haring basis, then I'll have two of them. So U1 to U1, energy going from U1P to U1K prime, and U to U2, energy going from U2P to U2K prime. Okay, it's a bit of algebra, but these are the expressions. Okay, these angles are again given here: alpha, beta, gamma. Alpha in front of P, K prime; beta in front of P, this P, and gamma in front of Q. Okay, and note that there is no U1 U2 product. So there is no energy going from U1 to U2 or U2 U1, because U1 and U2 are perpendicular. You take a dot product, that becomes 0. So it's nice. So there is an energy channel, transfer channel with U1 and energy transfer channel with U2. Okay, great. So let's try to see, estimate this, okay, using field theory. Now, once I can compute this using field theory, I can compute fluxes. Now, in this formalism, energy flux is the energy going out of the sphere of radius r. So this is radius r. So what is the flux? Is energy going out of all the modes from within the sphere to modes outside the sphere. So the giver mode P must be inside the sphere. The P must be inside and K must be outside. So that's what we got here. So K goes from R to infinity here, and P goes from 0 to R. So these givers are here, giver, and receiver are outside. Okay, and this for UA, which is A could be 1 or 2 in 3D, or in higher dimension it is 1, 2, 3, 4 up to D minus 1. Okay, so let's look at, and the total flux will be pi 1, which is for pi U1, and then pi 2, pi 3, and so on, pi U2, pi U3, and D minus 2. So by the way, pi 1, the U1 has different channel than U2 and U3, but U2 and U3 are similar energy transfer channels. Okay, so how to compute SU1 U1? So let's look at, so we have 3 U's, right? These 3 U's. Now these 3 U's. Now these 3 U's to 0th order, if you assume Gaussian, random variables, 3 random variables is odd order. Gaussian variables, average is 0. Okay. So to 0th order is 0. So we go to the next order. Okay. So like before. So what should I do? So I have this 3 U's. So each of them is U1 of K, U1 of P, U1 of Q. So like before, I am going to expand one of them using Green's function. So let's expand the first one, Green's function, and 2 legs, and the 2 legs here. So what should I do? If I don't join them, then it is 0. Okay. Okay. So if they're, for most of the combination it is 0, but for one combination, when I combine this guy with this guy and this guy with this guy, it becomes non-zero, because this product is correlation function. Okay, so that's what you got here. So we have C1P and C1Q. In fact, there are 2 integrals, and they are delta functions, and basically it goes away and you get product of these. I have the expression in the next slide. So these are vortex. These are vortex at both the ends. Vortex here and vortex here. And this factor 2. We should also know why this factor 2. One way to combine this is, well, there are two ways to combine. So there were two legs here. There were two legs here and here. So I could get, okay, so right now I use this with this with this one, and this with this. But it's also possible, so let's use this yellow color, this one, here and here and here and here. So I could combine this one and this one. Okay, and they will give the same combination, C1P and C1Q. So that's why there are two combinations, and both of them will give equal contribution, so this factor 2. Similarly, I can expand this using Green's function, and I get this diagram. I can expand this one with Green's function, I get this diagram. So I get three diagrams, each coming from the expansion of one leg. So U1K prime, U1P, U1Q. So when I combine all of them, it is behind this stuff. So it is K prime sine beta minus gamma. So it is the first one, okay? The first one is giving you some expression, okay? It turns out I need to also integrate the time part, so Tt prime, and like before, we assume that UK squared is large, and that gives you nu k squared. So since it is hidden behind, I'm going to write that expression. So we'll have vortex, these two vortex, sine beta, let's write it here, sine beta cos gamma, so I'm writing this one, okay, and this one sine beta minus gamma. So this is what I get here, and ik prime, this k prime here and k prime here. So all that product, and then we have Green's function, correlation function, but there will be integral with time. So the time integral will basically give you Cp at equal time divided by nu k squared plus nu pp squared plus nu qq squared. That comes below. Okay, so this is expression. So various signs and so on is coming from these two factors and that. And remember, I have to take the imaginary part here, so that I will go away. Okay, so in fact, the whole thing is pure imaginary. So if I take the imaginary part, I'll get pure real without I. Okay, so that's what we get from C1. We get similar expression for C2. The difference is that we have one U1 and two U2s. Okay, and so it turns out for when helicity is 0, HK is 0, helicity is 0. So it turns out expansion of U1 does not give you, will give you 0 value, but I can expand these two legs using Green's function and so on. So I get two diagrams, one for this leg and one for this leg, and which are given there. So that expression is given below. This one is quite nice, relatively. So I get C1Q, C2 of P minus C2 of K prime, bracket, divided by nu 2K squared, nu 2P squared, nu and Q squared. These are a function of K prime, K, P, Q. Okay, and these two are equal. These two guys, this K prime sin beta, then show that it is P sin alpha. Okay, so that's why you get K sin beta squared. Okay, so I can write this part as K sin beta squared. Okay, so this is U2, and we can see which is giving energy to whom. Okay, now we can also compute flux. as I said, how to compute flux. The giver is um, inside the sphere and receiver is outside the sphere. I integrate. It turns out we make some change of variable like this one. K is r divided by u. P is r divided by r is the radius of the sphere. Okay, r by u v, and q is r w by v. And bit of algebra, and then we get this expression. So for every component, I compute the flux, the respective flux, this guy. And there is a prefactor A, which is coming from this integration. So we have SD minus 1, sphere of radius d minus 1, SD d minus 1 squared 4, the two correlation functions which are being multiplied, CP, CK, and so on. So that is 2 divided by d minus 1 squared whole square. Okay, well, 2 divided by d minus 1 whole squared. So that is that. And two correlation function is k squared, k Kolmogorov squared, but there is a viscosity below. So that takes get rid of one of the square root, so you get k3 half. So that is A. And this integral you can do it quite okay easily, and that is that. So this integral is right hand side. If you A is unknown right now because k naught, this is not known, but nu star is known. There is a nu star below. Okay, so in fact this one has a viscosity sitting there below nu star. So this integral is known. This integral is known. So it turns out if you can do the total flux, which is sum of all these fluxes, and we have the constraint. The whole integral, well, by the A multiplied by the integral is J. So J plus d minus 2 JB is 1, and there will be prefactor A in outside. Okay, so I can do the integral, and if I do everything right, then I get k naught 3 half multiplied by a number equal to 1. K naught, so k naught 3 half some I equal to 1. Okay, this I will be function of SD d minus 1 da da da. So but this is computable. This is coming from all this algebra. It turns out, by the way, I forgot to say that this integral is convergent. This integral is a finite number. So there is no ultraviolet or infrared divergence which plagues some field theory calculation. This is finite. Okay? And we can solve it, and we can get Kolmogorov constant. For d equal to 2, there is only one component, u1. So we don't need to compute u2, and this left hand side is 1. Okay, in the inertial range, in the 5/3 regime, so d equal to 2, by the way, there's a interesting thing that if you force certain wave number, then there's a 5/3 regime and -3 regime. I'm sorry, I made a slight mistake. So there's a 5/3 regime in the spectrum, EK, EFK. So we have 5/3 shallow and steeper. This is -3, -5/3. So this regime is what we are looking at. Okay, I'm sorry to say this is 5/3 and this is -3. So this regime we are looking at, and this regime the flux is in fact negative. It is inverse cascade of energy. So we want the left hand side to be -1. Okay, so left hand side should be -1, and it turns out this integral is negative. Here is this integral is negative, and so from that you can compute Kolmogorov constant. It turns out if I do integral from 0 to 1, Okay, so that's how it should be, 0 to 1. I get Kolmogorov constant to be 1.19. However, in the experiments, numerical experiments, in some real experiment with soap and so on, people think that Kolmogorov constant is around 6 for 2D, and we are getting 1.19. So that's not looking very good. So it turns out I did by hand. So I do believe there is some issue. RG calculation maybe has some problem in 2D. Possibly we should, there's some non-local interactions is missing. Remember in Kolmogorov theory, in RG, we were integrating scale by scale, and that may not be the best thing to do for 2D hydrodynamics. So we are doing scale by scale. So it's not clear, and I think it's not clear to most people that how to do RG in a very consistent way. Cregnan eddy viscosity is negative, but RG is positive. So right now this procedure gives you 1.19 if I take 0 to 1. However, if I use my cutoff here, so if I use the lower wave number to be somewhere here, 0.22, this one, 0.22, then we get Kolmogorov constant to be 4.66, and which is okay, which is around close to 6, not quite 6. Okay, so for 2D, the Kolmogorov constant, I tinkered with this lower cutoff, which may not be satisfactory, but this tinkering is required in this framework. Okay. This is possibly because RG is not taking into account non-local interactions. In D equal to 3, we need to compute both two fluxes, U1 and U2. So we got original, and we use original U1 star and U2 star. K Kolmogorov is 1.43. Okay, that means nu1 is 0.1 and nu2 is 0.6. But if you use the star missing here, okay? If I use another approximation that since I have a typical viscosity in simulations, we take both of them to be equal, nu1 and nu2, so the viscosity should be the same. So I impose it. If that is the case, then K Kolmogorov will be 1.68. Okay, and this is more reasonable, 1.6 or 1.67, 1.65, 1.6 is the most believed Kolmogorov constant. Okay, so and it turns out for higher dimensions too, Kolmogorov constant is roughly following similar pattern. There's slight variation, but for D equal to 2, 3, 4, 3, 4, 5, the line is here. Well, I'm sorry, not here. This is the Kolmogorov constant. Here. Two of them. One is with the constant, both were equal. Another one is with original D1 and U2 star. In any case, these two procedures are slightly different, but the numbers are not too bad, not too different. Okay, so Kolmogorov constant for D equal to 3 is quite okay. So it seems okay. Now D greater than 3, KK nearly constant for D greater than or equal to 3. And this K Kolmogorov is not defined for D greater than or equal to 6 because nu1 star is not defined. Nu1 squared becomes 0. Nu1 squared becomes negative. So I believe D greater than 6, fluctuations are possibly uncorrelated, the zero flux, and turbulence is not generating energy flux. Now some more predictions from this theory. So we can look at this SU2. So I did compute this S as this SU2 U2. This was C1 of Q. So let's get some more space. So if you recall correctly, it is C1 of Q, C1 of P minus C1 of C2, sorry, C2 of P minus C2 of K divided by viscous term. Now we can make a change of variable to V and W, V and W, or V and Z. So what we are doing it here is we had KPQ, but make scale so that K equal to 1 and P. So I replace everything by divide everything by K. So this becomes V and this W, and this angle is gamma, and cos of gamma is Z. Okay, so that is Z. Cos of gamma is Z. Okay, so Z equal to 1 corresponds to gamma is 0. So Z equal to 1 corresponds to gamma is 0. So this is small angle. So this is 1, this is V and W. So this corresponds to V equal to this. So y-axis is V. Okay, I forgot. I have not written it well. Y-axis is V. Let's use red color. V. And this is V equal to 1. This is V equal to 2. V3 is 0. Sorry, V0. So here this V is greater than 1 is negative. What does it mean? And so when V is bigger than 1, this triangle V. So when V is bigger than 1, I get a blue curve which is negative. So this part is negative and this part is positive. So V less than 1 gives energy to 1. So this is energy going from V to 1. So when V is smaller than 1, it gives energy, but V greater than 1, it takes energy. Okay. So it tells us that energy goes from smaller wave number to larger wave number, right? So here larger one is taking from 1. So this is giving us the idea that energy transfer is local and forward. Okay, that's what it is. This picture tells us. It's interesting, this part. Okay, it turns out this one is all red, no? This all red. And this part in fact is strong. So in fact this, if you see the color notation, dark red is highest positive and dark blue is highest negative. So this part is quite positive. So that corresponds to what? V0. So what does V equal to 0 mean? V0 means this small and V W1. So V0 or V small means small v here. The giver is small. So for all givers, when this is all z's, so that means this angle is, V can take any value, any direction. So all these V's are giving energy to 1, like this. So these are non-local transfers coming from small v to 1. They are very large. So it turns out, this is in a preprint in archive which I wrote. So it turns out that there is significant energy transfer from small v to 1, and non-local transfers are also significant. Local and non-local transfers are comparable. That's what we see in 3D. Okay, so the dominant part you can see is basically this part for all dimensions, okay, uh, in d greater than, well, not all, d greater than equal to 3. In two dimension is slightly, well, no, it's quite interesting. So let's look at it. This part is negative and this part is positive. This is similar to what I showed before. So V is giving energy and V greater is taking energy, like that, local. However, you can look at this part is getting energy, negative, no? Blue is negative and red is positive. So this is getting energy. And what does it mean? So if I have 1 and here V small, okay, this V small, in fact this part is dark red, so V is getting energy from 1. So there is non-local transfer but in inverse direction. So 1 is giving to V, so this is a giver. Giver is taking, so this is a non-local negative transfer, and so this is what inverse cascade, okay. We get energy going from 1 to small, like that. So this is inverse cascade. So these modes are responsible for inverse cascade, and it happens for okay, interesting thing is this is for U1, okay. So this is not only for this for d equal to 2, but this U1 channel for all dimensions it happens. So this theory predicts that U1 channel and U2 channel have different types of energy transfers, and these are always non-local inverse transfer in U1 channel. Okay, that's an interesting prediction. So I should not say d equal to 2. So this is not correct. In the previous slide, it's not d equal to 3. So it's for any dimension. Okay. Now there's one more interesting thing. Is this fractional energy transfer. So the energy flux is the energy going from all the modes inside the sphere to outside. But we can say that, well, we don't think of all the modes, but think of a part of the sphere. So we say, well, I think of not the full sphere, this sphere from here to here, but I look from here to here, this part, or I make a sphere, this one. So modes here, a receiver is not up to infinity, receiver is up to RV inverse. So let's say V is half, 0.5. So this will be 0.5 to 1, and this guy will be 1 to 2. So this will become 1 to 2, and this is 1 to half. Okay, so we make this fractional energy transfer. Okay, and that gives us something very interesting. So let's see. So we can compute this. So the same formula where it was 0, well, energy flux formula, it was going from 0 to 1 for V. But I say, well, don't go from 0 to 1, you go to V to 1. And so you have U1 channel and U2 channel. Let's work it out for 2D and 3D only, okay? So in 2D, so V, if it is V0, then this is the full flux, which is pi is minus epsilon, okay? So this means pi is minus epsilon. This is pi is minus epsilon. Here in 3D and 4D, 5D, this is pi is plus epsilon, okay? So energy 2D, 3D, 3D, 4D, 5D is forward, but 2D is negative. Okay, we saw that. But if I look at well, 3D, if I make this sphere, well, this part, increase V, around half, this half. How much energy is flowing forward? Well, you can just mark it here, is around half. So you can say that the modes within the shell from 0.5 to 1 is giving half the energy to outside. So it gives you a picture, a detailed picture. Okay, so 3D is not so well, it's kind of expected forward, but in 2D is interesting. So it's negative, 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 negative. It's up to here. Okay, and this some I forget. This is around 0.225. Well, it's something like that. Here it becomes 0, and from this point onward, energy is positive. So in 2D, if I look at all the modes, I get negative transfer. Up to here, negative. But if I do up to 0.2, so or if I consider these modes, then I get a forward transfer. So if I just focus on all the modes in this sphere, 0.25 and onward. So if I make this sphere 0.25 and 1. So if I think of these modes, they are giving energy forward direction. However, these guys are receiving energy from this part. Okay, so non-local interactions in 2D or U1 channel is responsible for the inverse cascade. It's a pretty powerful prediction from this theory. And so that is for d equal to 2, 3, 4, 5 like that. We can also work with the fractional dimension near 2. So this is d equal to 2, d equal to 2, right? This is what we see. D equal to 2.1 is here, d equal to 2.15 is here, and d equal to 2.5 is here. It's hidden there, but it's around. Okay. So the point is d equal to 2.5. If I make a sphere, if I make a sphere like this, the energy is forward. But for d equal to 2.1, there is an inverse cascade. Okay, overall energy is flowing in for d equal to 2.1. But 2.15 is 0. Well, 2.215 is 0, and energy at 2.5 it is, well, anything above 2.15 it is positive. So 2.5 there is no energy going out of the sphere. So the critical dimension, or the dimension where the forward of DC, D less than DC, inverse cascade, D greater than DC, forward cascade. And DC is 2.15. Okay, the 2.15, the direction of cascade changes. Again, it's very interesting proposition. Simulation wise, I don't know how to check, but it will be a good thing to try it out. Cell to cell transfer, we can define this cell to cell transfer, which is energy going from any wave number shell to another shell. So here the giver is orange shell. So giver is, so we label it as S is greater than 1, is true. I take to the power 1 quarter. So S to the power m to S power m plus 1, giver. Orange is giver. And yellow is the receiver. Okay, this is receiver. Okay, and what do I do? So giver is, this giver shell P is residing in the giver shell. Okay, this is giver is, P is inside this region, P is here, and K is here, a receiver, and integrate. Okay, this is doable with field theory as well, bit of algebra, and we find that interestingly, for d equal to 3, you see, is forward. So what does it mean? So this is n minus m. So let's say n is m is 5. Then n is 5, it should be 0, no? I cannot give any money to myself, net money. But when n is 6, is getting energy, so it's positive. In fact, it's compared to total flux, it is 20%. Then I go to 7 is maybe around 7%, and it keeps going down after that. So most dominant transfer is to nearest neighbor around 20%. Okay, that's the field theory prediction in 3D. In higher dimensions, roughly same. In fact, this is interestingly, all dimensions have similar cell-to-cell transfer, d equal to 3, 4, 5. But d equal to 2, there is a forward transfer to the forward neighbor. So 5 gives to 6, 5 gives to 7, 5 is not giving to 8, okay, it's about 0 flux. But 5 receives from 6, 7, 8, 9. 5 receives from 9. So that's what is happening here. If I draw the diagram, so 5, it gives to 6, gives to 7, gives to 8, but it receives from 9, receives from 10, receives from 11. And this receipts, in fact, this goes on for all these modes. All these modes are giving energy to lower wave numbers in 2D, and that is responsible for the inverse cascade. Okay. So past work, there are not many, but some works. And this is by Fournier and Frisch. They do find change of cascade at d equal to 2.05. I discussed it, I find this to be 2.15, and they have solution which is 5/3, k minus 1. So this is not based on field theory per se, but EDQNM, which is not as rigorous as field theory, but similar formulas. So I think there's some similarities and there's some differences, and I need to look at it in more detail. There is also some simulations. For example, recently there is a simulation by Berera et al. And they find, so they did it for d equal to 4 dimensions. And this picture shows you the spectrum for 3 and 4. So I believe red is 4 and black is 3. Okay, and so they show that Kolmogorov constant is 1.3 and in 4D and 1.7 in 3D. Flux are also roughly equal. So this is kind of consistent with what I showed, that d equal to 3 and d equal to 4 or d equal to 5 also, things are not changing significantly. But d equal to 2 is different. Okay. So conclusion, d-dimensional turbulence k minus 5/3 is a solution, and it's a consistent solution. So it gives a faith in Kolmogorov solution. There could be other solutions. For example, equipartition is a solution, but possibly that is unstable for d equal to 3. So d less than 2.15 inverse cascade, d greater than 1.5 forward cascade, d greater than 6 equilibrium solution, that equipartition is equilibrium solution. By the way, please keep in mind equipartition solution is EKD minus 1, because every mode has same energy. Okay. And field theory provides valuable information about energy transfers. I showed you shell-to-shell transfer, fractional energy transfer, energy flux. We can learn that from this